Now we'll calculate the position of center of mass of a uniform hollow cone. Here if we consider a hollow cone, again by symmetry we can state that its center of mass will be located on the line which is passing through center and normal to its base. Now if we wish to calculate the center of mass from a particular reference point, we need to consider an element. For a hollow cone, certainly here we need to consider elements like strip rings. So let me take it in a different way. Rather than taking reference point at the bottommost point, here I take the vertex of this cone as a reference point, and at a distance x along the projector of this cone or along any length which is on the lateral surface, I consider a strip of width dx like this. Try to follow me what I am doing. I consider an elemental ring which is of width dx at a distance x along the lateral surface. In this situation, if I find out the mass of this elemental strip dm, your mass can be given by mass per unit area multiplied by the area occupied by this ring. Now in this situation, the area of this ring can be directly written as x sine theta if theta is the half angle of this cone. So this radius can be written as x sine theta. Now in this situation, dm elemental mass can be written as, if the total mass is m, it can be written as m upon the surface area. Surface area of this hollow cone can be written as pi r L. So it will be pi r. The length of the surface can be written as root of h square plus r square multiplied by the area occupied by this elemental ring, which in this situation is 2 pi x sine theta into dx. So here this is the elemental mass. If I substitute the value of sine theta here, you can see the value of sine theta I can write as r upon root of h square plus r square. So in this situation, this dm can be given as, this pi gets cancelled out, is m upon r root of h square plus r square into 2x. Sin theta can be written as r upon root of h square plus r square into dx. Here this r will also get cancelled out. Value of elemental mass in this case will be 2m upon h square plus r square into x dx. So this is the elemental mass for the ring strip. Here we can write, we consider a strip ring of mass dm as an element. Now, in y direction, if we wish to calculate the y coordinate of center of mass with respect to this origin, it can be given by 1 by m integration of dmy. You can see everywhere if we are required to find the coordinates of center of mass, it can be obtained directly by the relation 1 by m integration of dmy, or similarly x or z coordinates if required we can calculate. Here if we substitute the values, you can see this 1 by m dm we substitute from here, it is 2m upon h square plus r square into x dx. And again, if we talk about this y coordinate can be written as, if this is x, this is theta, it can be written as x cos theta. Y coordinate I'll write x into cos theta, and here cos theta can be given by h upon root of h square plus r square. This h upon root of h square plus r square. This is the way how I write cos theta. You can see this is cos theta. Just for clarity, I have drawn it separately. That this cos theta and the y coordinate is actually x cos theta. And if we substitute the limits of x, so x will be integrated for the whole cone from 0 to root of r square plus h square. Now the only job left is to integrate the expression. Here you can take most of the constants out. This will be 2h upon h square plus r square to power 3 by 2 integration of x square dx from 0 to root of r square plus h square. If we integrate this expression, you can see what we'll be getting here. This will be integrated as x cube by 3. So this will be 2h upon h square plus r square to power 3 by 2. This is x cube by 3 and limits will be from 0 to root of r square plus h square. Now let's follow it on the next sheet. Now here yc can be given as 2h upon h square plus r square to power 3 by 2 multiplied by, we substitute the limits, this will be same r square plus h square to power 3 by 2 by 3. So this expression will get cancelled out and finally we get yc is equals to 2h by 3, which is again a useful result. If we are having a hollow cone, so in case of a hollow cone of altitude h and base radius r, you can see that its center of mass is located at a depth 2h by 3 from the vertex along the altitude, or you can also write it at a height h by 3 above the center of its base. Now for the hollow cone, be careful about the results. Its center of mass is located at a height h by 3 above the base. So y coordinate from center of base, if required, you can write it at a height h by 3 from center, and from the vertex it is at a height 2h by 3.